All right, so I want to thank the organizers for inviting me to talk here, and I'm also going to blame them for picking me because my talk has nothing to do with wave turbulence, so it's, you know, it's their fault. I'll try to stick in some NLS equation at some point just to try to connect. All right, so the question that we're going to be looking at is a question of deriving effective equations from particle dynamics, from many particle dynamics. And the goal is to present a method that has been successful in doing such things for singular interactions, which are particularly difficult to treat. And then I will try to present some extensions and questions. And at the end, if you still have some patience, I'll show you a bit of technical proofs, but very light. OK, so here is the situation. We want to consider capital N points in space, so say the Euclidean space RD. And they interact with this pair interaction potential G. And if you want, you can add some external potential, capital V, scale like that. But it's not so important for the discussion, so I will kind of ignore it. Just say that if you want, you can add it back. OK, so just think of repulsive particles or repelling particles. And the interaction is simply an inverse power of their distance. So we will call that a Riesz interaction in general. And so you see here S is the parameter of the power, is typically non-negative, and you want it strictly less than the dimension so that the kernel is integrable near 0. So you can think of this as a fairly long-range interaction, right? Because, at 0 it's integrable, but at infinity it's precisely not integrable. So it's long-range interactions. When S is 0, you want to take the convention that S is 0 corresponds to the logarithmic interaction, so it's the log case. And this contains the very important Coulomb case, which is in all dimensions S equals D minus 2. Okay, so dimension 2 is log, dimension 3 is 1 over x. And so what we want to do is look at dynamics, where each point is going to move according to, so there are 3 proposals here. The first one is the gradient flow, in which you move according to the gradient of the energy, or minus the gradient, with respect to location I. And you divide by n, meaning you do a sort of average, right? It's like the point feels the sort of average contribution from the other points. That's why it's called mean field also in the end. Or you can look at conservative flows, which would be the same thing, but you multiply here by some antisymmetric operator. Or you can look at second-order evolutions where the acceleration is given as the average gradient. So that's really Newton's law, right? Acceleration equals the force. That's the most physical setting here, possibly. And if you want, you can add some diffusions. So here, WIT are independent Brownian motions. And beta is an inverse temperature. So when beta is infinite, it corresponds to the situation with no noise. And then you just delete these blue terms. Okay? So at first, I will only consider the case of no temperature, beta equals infinity. And later, we will add back the temperature. So what you want to do, so I will focus mostly on first-order evolutions, because that's the ones for which we have more results, honestly. So unless I say so, it's first order. And when I talk about second order, I will mention it. So let's say we can put all these first order in a general form like that. And so here M is a matrix. You take it identity, it's the gradient flow. And you take it antisymmetric, it's a conservative flow. Or you can take other matrices. But okay, so this is the general form. And the question you want to ask is, what is the limit of the empirical measure as n goes to infinity for each time? And you expect, of course, that this mu t, so it's some sort of probability density that's evolving in time that's going to solve a certain PDE. Okay, another point of view is you can take probabilistically, you write down a joint law on the particle configurations. So it will be called Fn. And let's say at initial time, it's going to be Fn0. So for instance, you can take it to be a Dirac at some initial configuration, or you can take a true probabilistic distribution. And you want to understand the behavior of the joint law at later times. So that thing also solves the PDE. And these are 2 points of view which are kind of equivalent in the end. So there's this very important notion of propagation of chaos, which says that, so it consists in saying that if your initial law is tensorized, so if it's a sort of IID particles with law mu naught, if it's in this form, then at later times it's approximately tensorized in the large N limit, okay, with some different mu, which is mu t now. Of course, this mu t here should be the same as the mu t up here, the distribution of the particles. And so if you have that, then you say that you have propagation of chaos. It means that even though the particles interact, there is still independence restored in the large N limit, which maybe at first is surprising, but can definitely happen. So in fact, these two things are kind of equivalent. If you can prove convergence of the empirical measure like this, then you get propagation of chaos. And if you have propagation of chaos, you have convergence of the empirical measures. And this, this inequality, this relation here should be understood in closeness of the k-point marginals, fkn. So f and k are the probability densities of having, restricted to k points. And these are the things that for fixed k will converge as n goes to infinity. So if you have any questions, you can feel free to interrupt, of course. I hope the setup is clear. So I want to say that looking at such questions is actually quite interesting and has many motivations and even possibly fundamental. I don't know. So one is certainly when you look at second-order evolutions, you're right in physics, Newton's law with, in particular, Coulomb interactions. That's one of the most relevant systems, in particular for plasma physics. And you're trying to derive basically a macroscopic theory from a microscopic classical dynamics. So that would be the dream. So more generally, these are all like kind of, with noise, you can consider these as Langevin dynamics, or overdamped Langevin dynamics gives you back first-order evolutions. The point vortex system in fluids is one instance of a conservative system with n particles in logarithmic interaction in the plane, so it falls right into this framework. Vortices and superconductors and superfluids are also of the same nature, with logarithmic interaction, but quantized vorticities, contrarily to classical fluids. Dynamics of agents in biology and social sciences, you often encounter such questions of passage to limits in ODE systems. Of course, the interactions are maybe more general, like less restricted than those. And more generally, you can think of running gradient flows or gradient flows with noise as a way to try to approximate minima, so to converge in long time to minima of interaction energies. You find that also when you try to optimize parameters in neural networks, which you can also see as interacting particle system, maximum mean discrepancies in statistics. And there's certainly also relations with other things that you find in statistics, algorithms, for stochastic gradient descent, variational gradient descent, etc. Okay, so with that said, I hope you're convinced that it's useful. And so now the goal is to try to pass to the limit rigorously, to take this large N limit. And I said the limit density should satisfy PDE. So we're going to try to first guess what the PDE should be. And so there is a general fact that this PDE is always going to have a form like this, like dt mu plus divergence of some velocity field times mu equals possibly this diffusion term. And why does that happen? Because whenever you have a Dirac mass that's moving, the time derivative of the Dirac mass plus the divergence of the velocity times the Dirac mass equals 0. So that's a continuity equation for the Dirac mass, right? So now if you formally put your empirical measures into this relation, and you look at what the velocity field is, and you replace the empirical measure with your limit, you find that formally you're just making a convolution. Right? So maybe I can go back to the first slide. Right, so if this is your evolution, right, you can view this as the gradient of G sampled or integrated against the empirical measure and then evaluated at xi. So you replace the empirical measure by the limit, that gives you a convolution. And so this is why you will find a relation of this form. And if you have noise, of course, you add the standard Laplacian term. Another point of view is you can write down what's called the Liouville or forward chromograph for the process associated to the. So now in terms of the joint law, the joint law itself solves this PDE in large dimension, right, in RD to the n dimension. It's also a dt plus divergence, blah, blah, blah. So in fact, it has exactly the same form. And then you can try to take the formal limit in that, or you can use what's called the BBGKY hierarchy. And you will find that if you assume independence, so if Fn is tensorized, if you make this independent ansatz, the mu that's associated will solve the same equation, right? So this is called MF, like mean field. We'll refer to it many times. So an example, if we're looking at Riesz interactions, right, and if M is identity, that corresponds to the dissipative case, then this is an instance of the fractional porous medium equation. So these kind of equations have been studied from a pure PDE point of view, if you want, and their regularity, existence, theory, etc., is also interesting on its own. But thankfully, there are some results around. So we want to pass to the limit rigorously, and you can see right away that this is not obvious because the thing is nonlinear, right? So in terms of the density, if you have here the empirical measure and here the empirical measure, you have to take limits in products. And that's not usually an easy task, especially if the kernel that's here is singular. So that doubles your difficulties. This is why it wasn't easy. In the second order case, then instead of describing things with the density of particles, you have to go to a kinetic formulation, and then you describe through density at position x, velocity v, right? So this is the density of particles. Position x, velocity v is called rho, and the empirical density is mu, is the first marginal. And then the formal equation is going to take this form, which is a Vlasov form, or Makin-Vlasov, or Vlasov-Poisson, if G happens to be Coulomb. So you find here you have a free transport term. Then you have the sort of electric field, you could call it here. Plus possibly the diffusion. Any questions? Okay, so I go back to my, this is the same. Some questions of how to prove these convergences. I want to review a few methods that have been put forward in the literature. The first one, which is goes back to the 70s, I think, with the work of Makin, is a trajectorial method. It works well when you have noise, but you don't need noise, really. You're going to compare the true trajectories of the particles to the trajectories of some fictitious particle that would be following the velocity field associated to your limit equation. Okay, so if you want the characteristics of your limiting equation. So you take two particles, start at the same point. One does the true dynamics. The other one does this sort of idealized dynamics. And you try to show that they don't separate very much. And that actually works well if, so K, I should have said, K is gradient of G. So it's the kernel. Should be Lipschitz. So for us, this is not going to work at all because we are considering inverse powers that are always singular at the origin, very far from being Lipschitz. And not only that, the gradient has to be Lipschitz. Yeah. There are n particles.
So in that true system, there are n particles. So what do you mean by a particle following the true dynamics?
Yeah, so your particle number I, for instance, it is going to follow the dynamics with those n particles. And then you're going to have a fictitious particle yi which follows a dynamics that's completely independent of any other particles. And then you look at the sum of xi minus yi squared. You sum over n. And you look at how that evolves in time.
There's an n particle dynamic compared with...
Well, you make a fictitious n-particle dynamics where they don't interact. Right? That's your fictitious system. Each of them just follows the characteristics of the PDE and doesn't look at the other particles. Okay? The true independent particles compared with the truly dependent particles, you measure basically the Wasserstein distance of the empirical measures. You differentiate in time, and it beautifully closes. You get a ground value. But you need the Lipschitzness of the interaction. Okay, second general line of thought is find a good metric. And people have been using typically a lot of Wasserstein distances of many kinds. A good metric that for which you have stability of your limiting PDE. So you look at first look just at the limiting PDE. What you want is that if you have two solutions, mu1 and mu2, to the limiting PDE, the time derivative of your distance, so here I called Wasserstein, it could be another distance. You want the time derivative to be bounded by a constant times the distance. And if that is true, then certainly if the two solutions start initially close, then at later times they will be closed by application of Grunwald's lemma. And so you'd better have that if you want to hope for convergence, because now what you're going to do is apply it to the empirical measure and the limiting measure. So that's are going to be your two measures. So that one solves the PDE. That one doesn't solve the PDE, but it solves something resembling the PDE. And so you're going to try to run the same argument and to basically take advantage of this stability, or you can call it weak-strong uniqueness principle. Okay, so that, again, has been working quite well. It allows to treat some singular interactions, but never as singular as Coulomb, for instance. So it didn't work. Final line of thought is relative entropy-based methods, which are appropriate when you have noise, when you have diffusion. Otherwise, they don't, they don't help you. So this is a definition of the relative entropy. So now you have your density Fn, your joint law, and you compare it with some tensorized law, say rho to the n. And here it's normalized. It's appropriate to normalize it like that. But that's otherwise the usual relative entropy. So it has a sign. It behaves kind of like a distance. So if you know that it's small, it means that you have convergence. And you can differentiate that in time. And what happens is that if you have pure diffusions, the time derivative of the relative entropy, if you just had diffusions, would be a negative term equals to minus the Fisher information. That's always the case. And that's beautiful. Then you see a decrease of relative entropy. And then you sort of treat the interactions as a perturbation of that. Right? So now you don't have just diffusion, you have the interactions, and it's going to give you other terms, and you're going to have to work quite hard to control these terms in terms of the relative entropy. So this is what was done by Jabin and Wang in this very nice paper, and they were able to treat the case where this kernel case, OK, is gradient G. I should have written it. Now it can be a bit irregular, but still not too irregular. So it still doesn't get you Coulomb, I would say, in general, except in the conservative case. In the 2D conservative case, which is barely singular. OK, so we're going to see those methods come back again. And in the Coulomb case, so I said there was practically not much in the Coulomb case, except 2D, because 2D is very special. In 2D, the Coulomb interaction is the log. And the log is barely singular, right? So you can sort of pass to the limit by hand in the nonlinear terms. And this is what was done. And then, so then I want to, I should mention something about the second order evolution. So as I told you, we don't know how to prove second order convergence in generality. But Auré and Jabin and Wang had proven convergence for some S that are small enough. So they don't really go all the way to D minus 2. I don't remember what they, depends on the dimension, but something like D minus 1. They're able to prove using something that's of the flavor of the Wasserstein metric approach. They're able to prove convergence, but Coulomb which is really the equation for, the situation for plasma physics, remains open, and it's an important scientific problem, I would say. People have treated the case where you have Coulomb, but with n-dependent cutoff. Right? So you cut off your interaction at a certain scale, depends on n. Okay, so now I want to talk about the modulated energy method, which is going to succeed at overcoming some of these obstacles. And yes, so originally I introduced this method in conjunction with a different problem, which maybe is going to resonate with some of you here, which is vortex dynamics in superconductors and superfluids. So this is a PDE problem in principle. You have two types of PDEs that you can write, and they are all for wave functions, if you want, or it's called order parameters psi, which are complex valued. And here we're in 2D, okay? So you go from the plane to the complex plane. And the parabolic version is dt psi equals, well, what you see on the board. And there is a Schrödinger version, which is a very particular NLS, right? It's a sort of particular cubic NLS, which goes by the name Gross-Pitaevsky equation in physics. So psi is basically the modulus of psi represents the density of superconductivity or superfluidity in your system at the given point. And the phase of psi is related to the superconducting current. And here I simplified, I looked at the simplest setting here. And there is some parameter, epsilon, which you can take small. Okay, so we're going to take epsilon go to 0. And the interesting objects are the vortices, which are the zeros of psi, which carry a non-trivial topology. So because psi is complex valued, you can write it in polar form. Or some of you would call it Madelung transform, right? Rho to the EI phi. And the degree of the vortex, if rho vanishes at a point called x naught, you look at a circle around x naught, you calculate the circulation of the phase, and that should be an integer multiple of 2 pi, otherwise the complex number is not well defined. And so that's called the degree. Okay, so vortices, typically, think of them as having degree +1, because this is what is going to happen in practice, because the higher degree vortices are unstable. And so we want to take the limit we want to basically extract the dynamics of these vortices when the PDEs evolve according to these formulas. This system has an energy, right, which is standard. And what you can prove is that when epsilon goes to 0, so what epsilon goes to 0 makes these vortices be really point-like. So, right, so it's like the regions where rho is not equal to 1 becomes very, very small, and you can think of your vortices as points. Epsilon is the sort of core size of the vortex. And you can prove that they evolve according to the gradient flow or the Hamiltonian flow. So gradient flow if it's the first equation, and Hamiltonian flow is if it's the second, of a logarithmic interaction energy. So basically, they behave like point charges in 2D. With this evolution. Okay, so if you fix the number of vortices, you let epsilon go to 0. This can be proven rigorously. Some math papers have done that. I didn't quote everyone. But. Okay, so then the question I was interested in is the situation where the number of vortices is not a priori bounded when epsilon goes to 0. It also blows up as epsilon goes to 0. So you have many, many vortices. And what you want to do is then you want to derive their effective dynamics, the dynamics of the density of vortices. So you see that this is very similar to the original question we started with, except we're not going to go through a discrete system. We're going to go straight from the PDE to a PDE. And the story is that, okay, in the end, you're going to get a fluid equation. So the vortices are going to sort of converge to something which solves the fluid equation. And this problem I discovered during my PhD. So it was in '98. And it took me 17 years to find the solution. So this is the result, 17 years later. What you want to do is you describe the system via the supercurrent, or superconducting or superfluid. So it's called a supercurrent. So it's the inner product in complex numbers of grad psi with I psi, which is in polar form rho squared grad phi. And okay, I'm writing a simplified version of the theorem, but you have to have assumptions on the initial energy, that there's no excess of energy, the initial data, the limit of the initial data is nice, and the number of vortices, as I said, is going to blow up as epsilon goes to 0. Then you normalize your supercurrent by n epsilon, and you find that this converges to a certain velocity field v of t, which is the solution of a fluid equation. So I didn't write the equation, but in the case where you started from Gross-Pitaevsky, it's the incompressible 2D Euler equation, legit, the one you know. And in the parabolic case, it's a dissipative analog of Euler that you can write down. Okay, so once you have that, you have convergence of the currents. You can also derive immediately the convergence of what's called the vorticity, which is the curl of the current, and which is going to weigh basically a Dirac every time you see a vortex. So this thing will converge to the limiting density of vortices, which is just then basically Euler in vorticity form. Just take the curl of Euler, you get Euler in vorticity form, or take the curl of the dissipative Euler, and you get your analog. And so how was that proven? Well, the idea was to introduce a suitable modulated energy, which resembles very much the energy associated to the system, because if you look on the previous slide, this is the energy of the system, right? It's conserved in the Gross-Pitaevsky case, it's decreasing in the parabolic case. And now, inside this, I stuck the limiting vector field V. You have to stick it in a gauge invariant way. That's the right way to do it. And you differentiate this thing in time. Okay, so psi now you take psi that solves the PDE. You take V that solves the limiting PDE, solution of Euler or the variant. And you differentiate that in time. You use, of course, the PDEs. And you see some very nice algebraic structures occurring, and then you need some estimates. There's all sorts of interesting ingredients in there. But finally, you manage to show that the time derivative of this is bounded by this, plus small terms. And thanks to that, you apply Grunwald's lemma, and this is going to show you that the supercurrent, which is essentially like that, converges to that. Right? So if initially this thing is small, it will stay small. And that's how it worked. And I used this term modulated energy by analogy with other terminology that have been appearing in the literature. So now go back to our discrete problem. What is the analog of the modulated energy in that context? That context should be actually easier. We sort of treated it after the other one, but it's a discrete problem. And so, Mitya Durax was the first one who applied, so sort of adapted the thing to the discrete context. And the idea is, again, you want to find some modulated energy. So it's combining the idea of energy. The system has an energy, which is the first one I wrote, right? Hn. Right? Maybe if we go back, go back a long time, there is an energy, this guy. Okay, so you're using the idea of energy and combine it with the idea of a metric. You want a good metric to metrize weak convergence. And so here is your metric. If you have two probability densities, mu and nu, you're going to want to form this double integral, which is like the energy of a system that would have density charge plus mu and negative density charge minus nu, and you put all these together and you see how they interact. So you count the total interaction energy. And this does make a metric. And because I know here you all know well Fourier transform and fractional Sobolev spaces, so you will recognize that this is just a negative Sobolev norm if you go in Fourier. So it's a good legit metric. The problem with it is it cannot accept Dirac masses. Because if you take a Dirac mass here, you will find G of 0 that's infinite. So in fact, the Dirac masses are not in the corresponding Sobolev spaces. So the idea was to sort of renormalize that by removing these singular terms. And so here comes the true modulated energy. Given a configuration xi, you put the empirical measure. Given a reference measure mu, you subtract mu here. So you do the same as there, but except you remove the diagonal terms. So this is the triangle here. You want to remove the self-interaction terms. And you can define, OK, now this looks very much like your original energy, but you see it's modulated by this mu. Right? It's like previously I had stuck in this V, now here you stick in this mu. When you have lost something, which is that this thing is no longer a genuine metric. In particular, it's not clear that it's positive. It's not positive in general. However, we can prove, with some work, that it does behave almost like a metric. So it does metrize weak convergence, etc. So that's the guy. And so now you understand the recipe. We're going to differentiate in time this quantity when you plug in for xn. So capital Xn is a proxy for the configuration. You're going to plug in the ODE system solution here. And here you're going to plug in the PDE solution and differentiate that in time. Okay? So when you do that, and here I have no temperature for now. So beta equals infinity. You do that, you find yourself with, some terms that have a sign. If you have dissipation, they're very nice, you can throw them out. If it's conservative, you will not find, you will just find 0. And so after removing these good terms that have a sign, you find yourself with expressions of this form. Okay, so now there's here a velocity field, which is the velocity field associated to the limiting equation. If you remember, you have to make a convolution. So here I should have put an m in case there is an m. But this is my velocity field, dotted with grad g x minus y, and then you integrate against that. And what you want to show is that you have a sort of Grandval amenable relation. So you want to bound the right-hand side by basically the modulated energy itself. And this, in fact, turns out to be just a functional analysis type of question. So you can remove, you can forget the fact that this comes from an evolution, that you have a PDE. Just give yourself some configuration xn, some probability density mu, and ask yourself if this relation holds. And this is the key. So you can prove this relation. It's a general functional inequality. This is bounded by Fn plus some small term, because here S over D, so if you remember, S is the power in the interaction, and it's always assumed to be less than D, so this is a negative power of N, so this is small. Here I put something that's like the Lipschitz norm of V, cheating a little bit because there are some more terms. And this is the left-hand side that we had to prove. Okay, so now we call this the commutator estimate for reasons I'll explain in a second. And this is really the key point of the proof. If you can prove that, then you see once you have introduced the right quantity, differentiate in time, plug that, you have Grandval, you're done. So this took a while to prove. There were several instances of the result, covering bigger and bigger ranges of S that you can treat. So now we can do all S less than D. And it also, so the best results to date are in two papers, one with Matt Rosenzweig, who's here in the room somewhere. We treated all S that's Coulomb and higher. So if you remember, D minus 2 is Coulomb. And now we can get this sharp error rate that we didn't have in the beginning. So this minus 1 plus S over D we think is sharp. And then a paper with Elias Hess-Childs, we have a different method that goes below D minus 2. Okay, I probably won't have time to get to that, so I'll just throw 3 words about what's involved in the proof of this. Electric formulation of the energy. The observation that there's a stress energy or energy momentum tensor structure hiding behind these terms, and also commutator estimates. So, yeah. No. It's not a D. No. Yeah, you can go to negative S's. You can go to negative S's. Then the interactions are not singular. But, yeah. So maybe if you want, if that troubles you, just put 0 here. Okay, just put 0. But -2 is a natural threshold. Yeah. Yeah. Jonathan.
Will you say what electric formulation is?
If I have time at the end.
Will you say what electric formulation is?
I'll say it at the end if I have time, or if you ask me the question.
What is electric formulation?
No, but you're only allowed to ask at the end.
That shuts everybody up.
Exactly. This keeps your attention until. Yeah. Okay, so why do we call this commutator estimate? Because when you spell out what these things is. So by the way, maybe I should say first, this thing looks plausible, right? Because G, remember, is an inverse power. When you take the gradient of G, you get an extra +1 in the inverse power. But when you multiply by a Lipschitz vector field, V of x minus V of y is like x minus y. So you recover the +1 that you lost. So okay, it looks reasonable, but you can't make a proof with that at all. You can't make a proof. So what you should do is you should break these double integrals and observe that you're doing the difference of 2 operations, one which is convolve with f. So f is this big distribution, right? Convolve with f, take the gradient, dot with v, and the other one is you multiply with v, take the gradient, convolve with g. So you're doing basically these things, but in reverse order. That's a commutator. And you can see it like that. This is a genuine commutator written. I don't know where my mouse went, but where? Hi. Hello. Can you come back? Yeah. Okay, so it's here. So it's a genuine commutator, except that in any case, you always have this problem of removing the diagonal. So even if you try to find off-the-shelf commutator estimates, you're going to be stuck because you're not in a classical setting, I would say. But commutator, this vision tells you that, okay, it's reasonable to expect that you're going to regain the lost derivatives by this commutation. Okay, so this is the key thing, and now it gives you the result you wanted. And this is the -2 gets here again. You see, but take it positive if you want. With no temperature, if your limiting PDE has a regular enough solution, in particular, you needed at least L infinity because my commutator estimate is L infinity. But you need a bit more than that. In fact, what you can see what you need. You need that this guy here is Lipschitz, okay? And the V is determined from mu by taking grad G convolving with mu. So this is the velocity field of the PDE. So you need this guy to be Lipschitz so you can apply the commutator estimate. And then you find that on any given interval of time, the modulated energy at time t will be bounded by the initial one plus this small additive error times exponential in time. And so in particular, if you know that this thing is initially small, then things will be small at later times, and I told you this thing does metrize weak convergence, so you will be able to derive from this that you have convergence of the empirical measures as you wanted, and this includes Coulomb, and this even goes higher than Coulomb, right? You can go all the way to S equals D, and if you wanted to go beyond S equals D, in any case, the representation here would be wrong. It's beyond S equals D, you have no convolution. The interaction becomes very short range, and it's not a mean field limit equation. It's a different regime. So there are extensions. First of all, we don't have to have exactly a Riesz power, like an inverse power. Our commutator estimates apply to a class of Riesz-like interactions. So you need, for instance, it's okay if the singularity is like Riesz at the origin, bounded above and below by some Riesz's, and also at infinity, and maybe bounded above and below in terms of the Fourier transforms. So it's a bit more flexible than that. You can even include some Leonard-Jones types potentials if you have dissipation. People have used the method, I mean basically the commutator estimate, to treat the quantum case also. You can also treat quasi-neutral limits with this, taking advantage of the fact that we have this sharp error rate. And this is the only moment where I'm going to talk about second order. we have been able to use the method for second order, but only in a particular situation, which is called the monokinetic case. Okay, so in the second order, you remember you have to describe everything through velocities, positions, and velocities. And the monokinetic assumption is the fact that you assume that at every given position, you have a unique possible velocity. So you have a velocity field, which is u of x. At any given x, you don't have a whole distribution of velocities like you would expect, like a Maxwellian or something. You really have a Dirac in velocities. And then the version of Vlasov that comes with that is a system now for density and velocity field, which is called pressureless Euler-Poisson, and which has some regular solutions for short times at least. So then you can make the modulated energy method work in this context by simply taking the modulated energy and adding to it a sort of modulated kinetic energy, where you make the difference between the actual velocity of the particle and the velocity field at the limit at this position squared. Okay? So when you differentiate that in time, things like completely nicely combine, and you find yourself with exactly the same commutator estimate terms that we had before, and then you apply the commutator estimate and you're done. So there's not much change in the proof, and so the result is this, right? If you assume that you solve Newton's law and that your initial data is monokinetic in the limits, and you have a sufficiently nice solution to this pressure Euler-Poisson, then you will have convergence if your initial modulated energy is small. Okay, so you will have convergence. I should have said it in position plus velocity. Okay, so now we want to add noise to this discussion, because so far I hadn't had noise. So it was observed by Riesz, Jabin, and Wang, that you can combine the modulated energy method with the relative entropy method. And how do you combine them? You should do it exactly like this. You should take the relative entropy. So now we're back to the description, the probabilistic description in terms of joint law, Fn, that you compare with the tensorized law, mu to the tensor n. You should divide by beta, and you should add. You see here, this is the average modulated energy, or this is the expectation with respect to the law Fn of the modulated energy. So when you differentiate that thing in time, you differentiate in time the relative entropy, you get a negative term, and then you get some terms that are singular when your interaction is singular. They are very bad because they look like Laplacian of the interaction. So you have a sort of Laplacian G terms, very singular. And when you differentiate the modulated energy, you also get very singular terms. Due to Ito's formula, for instance, again, they are like Laplacian G. But you see that here they miraculously cancel with each other. So you have very bad terms that cancel. So it's not actually a miracle. There's a reason for that. And so when you differentiate this in time, you're back to your same commutator terms, and you're done. So the difficulty is just to find the right quantity. This works only in the dissipative case. Right, so then commutator estimates, then you can treat all these Riesz cases as less than D. And one of their motivations that they had was to treat attractive logarithmic interactions in any D, actually, and prove convergence to the limiting equation, which is Patlack-Keller-Segel. And that works also, and if I had some time, I don't know, I would discuss it a bit at the end. One observation that we make with Matt Rosenzweig is that, in fact, this modulated free energy is a relative entropy in disguise. So you have to introduce something that's called we call a modulated Gibbs measure, which, given a density mu, takes basically the exponential minus beta, so you have to scale properly, times the modulated energy, times the tensorite measure mu, tensorite n times. So if you want, this is like a correction to the IID law, right? So the IID law would be mu tensorized n time. And this guy is the IID law with interactions. you add back some sort of Riesz interactions via this exponential, and then the k and beta is just the normalization factor that makes this a probability density. Okay, and then you compute, and it's in 2 lines. You find that the modulated free energy is actually just the relative entropy, except not of Fn relative to the tensorized, the IID law, but relative to this Riesz interacting law. And that's the thing you're measuring. You're comparing to something that's a better description of the system, in fact, because it's corrected, it contains the interactions. Plus some constant, which is small, so you can just forget it. And so when you differentiate this in time, when you differentiate a relative entropy, you know that you're going to get a Fisher information. And here you find it. It's the relative Fisher information relative to this modulated Gibbs measure. So this is the natural structure now. And this is why the computation works. You get this. This has a sign. And then you get your commutator type terms, which you can control, and you're in business. So one remark is that, in this whole story I've told you, you see that you apply Grandval's lemma, and then at the end you get an exponential in time times the initial data thing. And so it's a bit sad because this doesn't give you convergence for a long time, right? So it doesn't give you uniform in time convergence, which would be a desirable feature. So one of the questions at this point is, can we try to get global in time convergence? And one of the possible ideas is, well, you could try to take advantage of this relative Fisher information to not throw away this negative term, but use it. So in fact, if you could use it and prove that it's bounded from below in terms of the relative entropy with some uniform constants here, then you could get a Grandval relation of this type, and now you'd have a negative constant, and you'd be in business for uniform convergence. However, this functional inequality that you need here, so we call this a uniform modulated log-Sobolev inequality, seems very hard to prove, and it's not clear that it's always true. And we were only able to prove it, so this is work with Matt, in a particular case of dimension 1, so d equals 1, with some convexity, some added convexity related to the shape of mu t. But okay, I think this is an interesting open question, let's say. Another point of view that we've pursued was use the decay of the solutions to get a long-time convergence. Because, you have a purely repulsive system. So all your particles are together at the beginning, and what are you going to do in time? They're just going to spread. Because you're in whole space. If you have no confinement potential, they just spread. So the density goes to 0. What else can you do? So you can try to quantify how fast it goes to 0. So this is what we did when you have noise. In some Riesz cases where S is less than d minus 2, we proved that it converges, it decays like an inverse power of time with this particular power. And now what you do is you look at your commutator estimate, and you try to see, this constant that was in front that depended on the velocity field. You try to see how it depends on the actual decay rate. And so here you see that it depends like that. So you're going to get some negative power of time. And when you put that in Grandval, suddenly things become integrable. For all time, you don't have to pay an exponential CT. And so you can get a uniform result. So this is uniform result. So for now, it works only dimension bigger than 3 and S less than d minus 2, unfortunately. I note that here there was some talk about LDPs around dynamics the other day. So there is an LDP result proven by Elias Hess-Childs in this context. And then another situation where we were able to get uniform in time is when you work on the torus. Because on the torus, instead of the solution going to 0, it's going to equilibrate to uniform density. Because what else can it do? It's repulsive and spreads, goes to uniform density. And because you're on the torus, you can even show that it goes exponentially fast to this limiting density. And all the derivatives are going to be exponentially small. So again, you plug that into your Grandval, and you can get a uniform in time convergence. So this is what we did there. And then, I'll say just a word about the attractive log case, because that was also fun. we studied this problem that was first studied by Riesz, Jabin, and Wang. That was one of their main motivation. So you look at the torus because it's simpler, and you have to periodize the logarithmic interaction. So you solve instead this fractional Laplacian relation. And that becomes the equivalent of the attractive log gas, but on the torus. So again, you have the uniform solution. It's always a stationary solution, but now you can see that it becomes unstable if your temperature is not large enough. So if beta is not small, so above beta S, mu unif can become unstable. And when you run the modulated free energy method, then you find yourself with two terms, the relative entropy and the modulated energy, but now it comes with the opposite sign because the interaction is attractive. So what you need to do is you need to show that this attractive part here, you can actually control it by the relative entropy. And this is only proven so far when beta is small enough. So again, if you have sufficient temperature, so beta less than beta I, like beta inequality. So we proved that. So you can call that a modulated log-Sobolev inequality. And then you can close the thing. And one of the open questions is actually whether these thresholds of temperature are the same, for instance. So this is work with Antonin Chodron de Courcel and Matt Rosenzweig. So we showed that if you start close enough to the uniform solution, so here it's measured in the sense that the log of the initial data is small, so it's close to 1, then you will have uniform in time convergence in this relative entropy sense if you are at small enough beta. So you need a certain amount of temperature. And remember that if beta, on the contrary, is large enough, you will have even blow up for your limiting solution. That's Patlack-Keller-Segal. Another thing that you can observe on this particular problem, which is interesting, is that you can't always expect uniform in time convergence. And here what we do is we exploit the fact that the uniform solution becomes unstable. Right? So you can start very close to the uniform solution, and then you can sort of branch out away from it and use that to show that you cannot always have a uniform in-time convergence in relative entropy. OK, so this is where I wanted to get before Jonathan's question. And so we can finish, and I can take questions. Thank you. I think Jonathan has a question.
I can't even remember what the term was. What's electronic?
Yes, the
Something or
electric
another.
formulation.
Current formulation, something.
OK, so this is something that has been a quite useful point of view on this whole problem, which is that when you have your interaction energy, right, and you have a distribution of charges F, so F contains the empirical measure, maybe contains your negative background. So this is the kind of energy you're looking at, some double integral convolution. So what you want to do is you want to introduce what physically would be the electric potential. The electric potential, if you're in Coulomb, this is really the genuine electric potential. You convolve F with the kernel, right? And it solves, in the Coulomb case, it solves Poisson's equation, minus Laplacian H equals F. So now you can rewrite this thing. You see that you have one convolution. You can rewrite as HF. And then F. OK, but F is the Laplacian of HF. And then you apply integration by parts, Green's formula, you find yourself like that. So this is the electric formulation. You rewrite a sort of sum of pair interactions or a double integral into a single integral in terms of the electric potential. And so actually gradient of H is physically the electric field. So it's the Dirichlet energy of the electric potential. And so with that, you get some mileage. And so I have here in one slide is the proof of the commutator estimate if you didn't have Diracs. So if you didn't have this problem that you have to renormalize, remove singularities, in one page using this electric formulation, you can see that you have this particular structure that comes out, the stress tensor structure. You can rebound.
Sylvia, thank you for that fantastic presentation. So that probability current in 3D for the Gross-Pitavitsky equation, it's given by what? Because that's the interesting situation for the physicist.
Yes. So what do you call the probability density current? You mean the J?
The norm square of the wave function times the gradient of the phase.
Yes. So this guy, J, right? What I call J.
Yes.
Yes, so in 3D, it's exactly defined like that. It's the same.
Yeah, and it's solution of what?
So in the limit, the
yes.
3D Euler equation, 3D incompressible Euler equation. It's in my paper. It's proven. In a regime of large number of vortices, but which, by the way, I think physicists knew all along, right? They tell you,
yeah,
take the Madelung transform, you get the Euler equation.
So the incompressible Euler equation is like a scalar equation. This is what you are saying.
Now, the incompressible Euler equation
is
an
not
equation
a vector.
On a velocity field, no? You have a velocity field. It's a vector.
Yes, but the wave function is a scalar, so you are saying...
No, the wave function is a complex.
Is a complex scalar function.
Yeah.
So it's given by the Gross-Pitavitsky equation, and you are saying that that superfluid current is...
But this, you form a vector from your psi, you form a vector now, right? You take your psi.
Yes, but at the end of the day, this is a solution of a scalar PD, the Euler equation. Yeah. Oh, yeah.
No. You have to take your transform, right? You take your scalar, what you call your scalar equation, complex valued. You take the Madelung transform, and the velocity field that's appearing in the Madelung transform converges to the solution of Euler.
Okay, I don't get it, but...
I think this is what you'll find in physics books. I mean, yeah, I see people nodding, so yes. Vlad.
Before Jonathan again. Any other questions? What? Oh.
Vlad has a question.
If something bad happens to the limiting equation,
yes.
Can one lift that to something bad happening at the limit of the particle systems?
It's a good question. Maybe.
But are there such results?
I think maybe for a path like Keller-Segol, people have tried to use the blow-up to do something, but there's not many such results. The results are more in the other direction, right? It's conditional. If you have a nice solution, then blah, blah, blah. Which, by the way, I mean, if you look at you and Zahir's results, it's like that, right? You need to have, you start from the fact that you know your limiting solution is nice, exists, and then you use that to prove convergence. Saint-Raymond's work is the same. But conversely, I haven't seen many results.
I was going to ask a similar statement, which is that in all of this, there are a lot of assumptions about the behavior of the mu equation, I guess, as a measure. But with the beautiful structure that you guys have constructed here to have this sort of nice modulated energy, you kind of threw away the interaction potential at the beginning. But if your particles were constrained in some way or had to live on a manifold in some natural sense that you would think of, obviously, spins or something in a plasma, or how much could that sort of gradient structure or natural energy estimate structure be propagated if you were to have nice sort of underlying geometric constraint structure?
I think it would be okay. I think it would be okay. It's just a bit more annoying to handle, but I don't view that as a real obstruction.
Okay, one last question. So, Sahar, you're fighting with Sahar. Okay, sorry.
Maybe it's nice that you're on this slide. So this and epsilon is going to infinity, epsilon is going to 0. Is there a relation between them? Is there a scaling law?
Yeah. So I put that a bit under the rug, but there are some assumptions on how fast it goes. Okay, and you need it to go. Okay, you need to go to infinity, but not too fast, because otherwise you're gonna have many vortices, and then your limit could have rho equals 0. Right? And then you could have this. So there's a range. No, there's a range that's acceptable. And then there is a limitation for my result on Euler's equation. Is I need, and that's really a technical point that I've never managed to overcome. I need n epsilon to grow faster than log epsilon. And log epsilon is a natural scale in this vortex business. But otherwise, yeah, it should be true for any n epsilon goes to infinity, not faster than 1 over epsilon squared. Because you have more than 1 over epsilon squared vortices, you just destroy superconductivity, and your limit is. So there's a natural range.
Sorry, one more question. So I always like to understand things lots of ways. So at the very beginning, you said that you thought that the Lagrangian perspective was dead because it wasn't globally Lipschitz, right? Mm-hmm. And I wondered if, we have good Lyapunov control around the singularities that keep us from spending too much time there, and is locally Lipschitz. Can you translate it? Have you thought about trying to translate any of these ideas back into the Lagrangian perspective where you're following the particles? Interesting.
Maybe it's interesting, but I think that the point of view was a bit like precisely you don't want to follow the particles. That's the wrong attitude, right? You want to have a thing that's robust and that doesn't need, for instance, a lot of the proofs of Jabin, Auré, and stuff, they have to show that the particles have a minimal distance. And that makes you die, you're dead in very singular cases. So you want to not have to look so precisely of what the configuration is doing, but have a quantity that's more global. But I'm not saying it's not interesting. One could try to go back. I don't see interesting insight that would be gained from that at first glance like that.
Okay, so you have a question? No. If there are no any more questions or comments, let's thank Sylvia for a beautiful talk again.